Let's just apply all of this again, except a little bit harder. So we're given 3 chemical equations here. We want to find the equilibrium constant for the first one. And ultimately, we just need to look for similarities between the 2 equations that we know K for and the one that we don't know K for. So how can I manipulate these other equations to make them into that first equation? Or maybe even better, like this first equation has CO2 in the products. Which of my other expressions has CO2? The second equation. It's in a product though. So we probably need to reverse that equation, especially since CO2 is not found anywhere else. So I'm going to take this one and we'll reverse that one. And then if the coefficient was different, then I'd need to do something else. But the coefficients are the same, so I'm not going to worry about it for now. We can look at a second one. It's like here we got 3 hydrogens, 3H2. And we got H2 there, and we also have H2 in the third equation. Now, I already decided I'm going to reverse that second equation. And maybe we should even put a single line through that and rewrite it as the now reversed. So now there's the CO2, there's the H2. Do I need to do anything else to that one?
The only thing I noted was the H2O on K1 and K2.
Yeah. So by reversing this one, which we already did, there's H2O here, or now here, right? So now I got H2O in the products, which is where we needed it. Is there anything that we don't want in our final equation? Yeah. And now since those are on opposite sides, those will cancel out when I add these 2 expressions together. So now K, since I reverse it, 0.0 times 10. Oh, that's easy. That'll actually just be 10 to the negative 5. So now if I add these 2 expressions together, I should get the expression that I don't know the equilibrium constant for. Because these will cancel. My H2s will add. So I'll get my 3H2. Methanol's already there. And so when I'm adding these together, I multiply Ks. So my K for the negative 2 times K3 should give me K1. $140. And is that reaction going to favor products or reactants at equilibrium? K is larger than 1, which means that everything on top of my equilibrium expression will be bigger than what's in the denominator, products over reactants. So yeah, it'll favor the products. Cool. And now we need to address some technicalities. So equilibrium expressions can be expressed in terms of concentration or pressure. And they are not quite the same, but there is a predictable relationship between the two. Part of the issue is if you have a reaction where the number of moles of gas changes, then the pressure necessarily changes. Or could change, or the volume changes. Because we're creating more gas or we're creating less gas. So it's dependent on all of the same things that gas laws are. So we can't express this equation as Kc or Kp necessarily, but we can create a relationship between the two. So what we can do though is we can say molarity. What is molarity? Moles over liters, or moles divided by a volume. Moles per liter is usually what it is, but it could be I guess that would make it millimolar. It would technically be millimoles per milliliter. And then in the ideal gas law, PV equals nRT, I have volume and I have number of moles. And so if I rearrange this, P over RT is equal to N over V, or is equal to molarity. So while my pressure is proportional to concentration, it is dependent on the temperature when it comes to gases. So Kp versus Kc, right? Kc is expressed in terms of concentration. So this would be concentration of C raised to the C, concentration of D raised to the D, concentration of A raised to the A, concentration of B raised to the B. But if I want to express this in terms of pressure, I can replace now, because I said concentration is equal to pressure divided by RT, I can replace all of these concentrations with P over T, not A, C, D, this is still raised to the C, this is still raised to the D, but there's a lot of stuff that I can sort of factor out of this because R is the same, it's a constant. And temperature for this reaction would be the same for everything also. So R and T are constants. And so everything that's being multiplied by R and T, I can take that out. So I can get pressure of C, and I can move these exponents over. Pressure D, pressure of A, pressure of B. Now this is times 1 over RT raised to the C plus D. This is 1 over RT raised to the A plus B. If we had more reactants or more products, then we would just keep adding on to that. We can take this one step further, and we can combine this to be a single factor to get pressure of, oh, and actually, we can also combine this. The pressures of the products divided by the pressures of the reactants, that's Kp. The goal here is to relate Kp and Kc. So now this is Kc equals Kp times 1 over RT raised to the, CD, C plus D minus A plus, I need a little more room. C plus D minus A plus B. And then we can go even one step further and take all of this and just call it change in N, which is number of moles of gas. Because if we had more C, D, if it went E, F, G, if it kept going, it would be all of the moles, or all of the coefficients, really, added together, minus all of the product or reactant coefficients added together. So what happens then? Actually, should we wait? No, we'll do it. I'll show you in the example. And then even just one step further, and we can rewrite that as Kp. So if I switch the RT to the other side, Kp equals Kc times RT, raised to the change in the number of moles of gas. So this is the number of moles of gaseous products and reactants. So if there was something in the equation that was aqueous, that wouldn't get included. We probably also wouldn't be expressing it then in terms of Kp, but so this is the expression. If we look at an example, Kp is equal to Kc times RT raised to the change in N. I don't even really have to plug any numbers in. How many moles of gas are in the products, and how many moles of gas are in the reactants? 2 and 2. So this delta N would be the moles of gas in the products minus the moles of gas, so 1 plus 1, in the reactants, so it's 0. So this is Kc times RT raised to the 0. So what's Kp? The RT part becomes 1. Anything raised to the 0 power, this all becomes, well, that's kind of the same thing, but I meant to do this. This all becomes 1. So Kc is equal to Kp. If the number of moles of gas doesn't change, Kc and Kp are the same thing. So Kp equals 6.2 times 10 to the second. It's the same thing. All right, so up till this point, we also haven't talked about units for K because K doesn't have units. There's some kind of hand-waving simplification that happens when we're talking about or introducing equilibrium constants, because at first it doesn't really matter. Eventually, if you do more like inorganic or analytical chemistry, it might matter. But when we're writing out these equilibrium expressions, they're all with reference to some standard. And in that standard, as long as we're using, the standard is in molarity or atmospheres. So as long as we're using units of molarity, this is 3.7 molar divided by 1 molar. And so the units cancel out. So as long as we're using molarity and partial pressures in atmospheres, there's no units for K. So under which circumstance are Kp and Kc the same thing? So if A plus B is equal to C plus D, Kp and Kc are the same thing. Really like this kind of question because, I mean, here we're not given a temperature, but if I gave you an expression and said, actually like this one, right? If I gave you a temperature, R here is, I believe, should be 0.0821 atmosphere liters per mole Kelvin, because it came from the ideal gas law. So if I give you R and I give you the temperature, you could just calculate Kp. But if you know that Kp and Kc are the same, as long as the moles of gas stays the same, then you don't need to do any calculations and you could just write it in. So it's possible to answer if you know the shortcut, and possible to answer if you don't know the shortcut. Look at that. This was asked on Tuesday. What about solids and liquids? Solids and liquids in a reaction, their concentration is unchanging. And actually, as the book explains it, that's because the solids and liquids aren't compressible. So the volume doesn't change. So as long as the density stays the same, which would be weird if the density changed, I guess if there's a phase change. But if the density stays the same, then the concentration is always the same. It's not spread out in the solution. So when you have a solid and a liquid, the concentrations are constant, and so they don't get included in the equilibrium expression. Because if the concentration can't change, then it's not going to affect the rate. So and actually, the other thing for water, what's the molarity of pure water? I think it's like 55.5 moles per liter. And if you have 1 liter of water, it should weigh about 1 kilogram. So you can calculate how many moles is in that 1 kilogram divided by liters. Turns out it's like 55.5. So if you're doing something in an aqueous solution, that concentration is not going to change because it is the whole solution. So when we're writing out an equilibrium expression, gonna find our solids or liquids, but K, C in this case, H plus times HCO3 minus divided by CO2. So water's not included. What's the equilibrium expression here? Yep. Just the concentration of carbon dioxide. And what if it was? So even if our products are solid, just put 1 in. Still not included, just 1 divided by. Oh, yeah.
Is it basically like if a solution is not homogeneous and you want to exclude liquids and solids? Is that like one of the main reasons why you do that?
Is that why? Is that the case? Yes. So like when a solution's not homogeneous would be when you have liquids or solids. The reason is because the concentration doesn't change.
What if we had like all liquids?
Huh. Or all solids. I was trying to think of an example of all solids. The concentrations wouldn't change, so we'd have to use something else to express the equilibrium. Because there are situations, so there are situations where you, in organic chemistry, will use 2 different phases. You'll have an organic phase which doesn't mix with an aqueous phase, so in that sense you would have 2 different liquids. But it's not in the liquids themselves where the reaction happens, it's at the interface between the 2. So there must be a way to express that in terms of concentration or pressure, or what's behind all of this is activity, which we don't get into any more than that. That's a good question. I'm going to look that up later. What happens if you have, yeah, you can't. At least in terms of this class, you can't. Would there even be an equilibrium, though? Because one of the things that you can do if you want to drive an equilibrium forward, if you have a product that is a gas, then you just continuously remove that from the solution. Or even if you have a product that is a solid and you can filter that from the solution to remove it, you can push reactions forward by essentially removing that from the reaction. And especially in terms of an aqueous solution, that produces a gas, it'd be pretty easy to remove that gas from the solution because you do, in a sense, have a homogeneous or a heterogeneous mixture. I think because it doesn't, yeah, I don't have any examples of a liquid reacting with a liquid. That's going to haunt me. It'll haunt me until I find the answer. And then I'll tell you guys on Monday, if I find it by Monday. So for which reaction does Kp equal Kc? Kp equals Kc when the moles of gas are the same. And so when it comes to K, we ignore all of the solids, we ignore the liquids. So this is 0 moles of gas, and this is 3. This is 3 and 3. This is 2 and 1. Because again, Kp equals Kc times RT raised to the change in number of moles of gas. And so if that's 3 minus 3 equals 0, then RT becomes 1. Oh, excuse me. Okay. Good, we do one calculation. Oh, and I didn't even get to show you guys this. So the most direct way to determine the equilibrium constant experimentally would be to measure concentrations of reactants and products at equilibrium. So if we can measure those, then we can write an expression. Oh, good. I mean, I guess, oh no, they give us concentration units anyway. HI squared over H2 I2. So this is 0.78 squared over 0.11 times 0.11. The equilibrium constant is I did look up where K comes from, why we use K for constant. It comes from the German coefficient, which starts with a K. Oh, it's just 50. All right, so you just write the equilibrium expression, making sure that, at least here they gave us in terms of concentration. If they'd given us partial pressures, then we need to look and see, do I need to convert this? Because they asked for Kc. But if I'm using partial pressures, that's Kp. We're okay here because the number of moles of gas in the products and reactants is both 2. So even if they gave us partial pressures, it would still be the same as Kc. And then they have this slide of, what happens if we start changing concentrations? No matter what you do, it always will come back at equilibrium to K. So what I did, because I was again thinking about these indicators in lab and how we're able to switch concentrations, or how we're able to move that from one side to the other. So here I've got a reaction, my indicator with the hydrogen on it is red, and it becomes yellow when it doesn't have the acid on it. So basically, if you add base, it becomes yellow. And so like if I change any of these, like if I make this 12, oh, right, that's right. This one first. All right, so if I change any of these, and really what you're doing in this lab is you're mostly changing something other than the species that makes the color. Although you could change that also in theory, right? So if I change this to 12 or 13 or 14, or if I make this anything else, right? That changes K and it throws off this equilibrium. Now when it wants to come back to equilibrium, that's what I have over here. If I can manipulate the H plus concentration, so say we add some base, drop the base as it were. Oh. Nope, I didn't finish this. Because if this changes, then this concentration of the indicator should also change. As a more complicated expression. Dang. What I wanted to show that is if I increase the H plus concentration, you see that it shifts the reaction over to the left. Now there should be some corresponding decrease in this indicator concentration also, which I didn't end up calculating. But I think the point stands. Decreasing H plus will pull the reaction over towards the H plus. Increasing the reaction, H plus will push it over to the left. All right. I will do my best to get everything